trigonometric equations. So 5.2, we were verifying identities. So we learned the identities, but 5.3, we're actually solving the equation now. We're going to start with a warm-up. This one is not in the book. If you were looking at the book examples before we started this one wasn't in the book. But there's questions like this in the assignment, so I thought I'd throw one in there for like a warm-up. Just says verify that the x values are solutions of the equation. So to verify, I'm going to put x equals pi over 3 in. And show that that does equal 0. So this is the same thing that you were doing in your 5.2 assignment where you only stick to one side. And I've got 2 cosine pi over 3 minus 1. What is the cosine at pi over 3? 1/2. So 2 times 1/2 is 1 minus 1. That is 0. It works. There. I verified that that is the solution. So question B, 2 cosine 5 pi over 3 minus 1 equals 0. So I'm going to work with the more difficult looking side. The cosine at 5 pi over 3 is 1/2. And I get 0. It's verified. So there's a few questions at the beginning that are like that. That's all you have to do is show that it equals one side. Notice how I'm not solving an equation. The rest of the homework, we will be solving the equation. So there's different methods that you could use to solve these equations. And it's not going to be like the directions say, solve this by collecting like terms. You just kind of have to figure out what method you should use. So I'm going to show you where I would use different methods. Collecting like terms, that just means like, so here's the equation right here. I've got sine x on both sides. And you guys know if we have sine x on both sides, we should gather it all on one side. So I'm going to add sine x so that I have 2 sine x plus square root 2 equals 0. Then I'm going to subtract square root 2 and I get 2 sine x equals negative square root 2 divided by 2. And I get sine x equals negative radical 2 over 2. You may be asked one or the other. So question A, I'm asking you to find within the interval of 0 to 2 pi, what x values would make sine negative radical 2 over 2. So this is the stuff that we did back in chapter 4, where from 0 to 2 pi, there would be 2 places where sine was negative. What would be the reference that would give us a pi over 2? Pi over 4s. And to get it into the third and fourth quadrant, we would need the 5 pi over 4 and the 7 pi over 4. Yes. Yes. Figured it out saying out loud. Yeah. Okay. So that's stuff we've done before. And some of the assignment will say to do that. And then some of the assignment won't say to do it on the interval. If it doesn't say to find it within the interval, then what it means is general solutions. So you know this this answer at 5 pi over 4, that would be the exact same location if I went around the graph more than once, or more than twice, or more than 3 times. I would keep landing at that every single time it went around another how much? What's the period for sine? Right. So every 2 pi that I go around, I get another terminal side that would end at 5 pi over 4. So when we talk about the general solutions, we're going to have one general solution at x equals 5 pi over 4 plus 2 pi n, where n is an integer. And we also have a solution at 7 pi over 4, which we can use the period and go around multiple times. So we're going to add on 2 pi n, where n is an integer. So this would be the general solutions, every single answer that would ever work. Because the book used n.
So it doesn't really matter.
Well, let's all use n because then we have to type it in Canvas. So with the asymptotes, they use k's, and then with this, they used n's. I think it's just to keep it separate. So this is a different thing, but really you could use whatever variable in real life. You could use whatever variable you want. Okay. All right, the next one, I would solve this one by what's called extracting square roots. So we got 3 tangent squared x minus 1. I'm going to add that 1 to both sides. Divide by 3. And then I would need to square root. Tell me out loud, what happens when you square root? We need a plus minus. Yep. So I get tangent x equals, and I'm going to do this really fast, amazingly in my head, negative or positive negative square root 3 over 3. So the first part of this says in the interval from 0 to 2 pi. This is plus minus. That means we get 4 answers. Every single quadrant. So all I really need to know is what is the reference angle, or the first answer, actually. Pi over 6. That's what I thought. And so I have all of them, and I'm going to put them in order of all the pi over 6s in order for one time around the circle. So how do we do the general solutions for this? What is the period for tangent? It is pi. Period for tangent is pi. So over here, if I say pi over 6 is my first answer and I add pi, that will already give me my third answer. So when I write the general solutions, I'm not going to have 4 general solutions. I'm going to have one of them that's x equals pi over 6 plus pi n, where n is an integer. And I will also have the second one, because if I add pi to that, I will get the fourth one. So that is 5 pi over 6 plus pi n, where n is an integer. Questions? Okay. We might need to use factoring to solve some of these. If you are going to solve something by factoring, there is something that you have to have first. If you're going to solve by factoring, does anybody know what I have to have in my equation to solve by factoring? Well, I have an equation, so what needs to be in the equation? I have to have a 0 somewhere. It has to equal 0 or you can't solve by factoring. Has to equal 0 first. If it doesn't equal 0, you are either going to solve by factoring wrong or you can't solve by factoring. I've just had people do it when it doesn't equal 0 and then they mess up. Okay, so I'm just going to rearrange. I'm going to get cotangent x cosine squared x minus 2 cotangent x equals 0. Now I can factor and solve by factoring. First step of factoring, Always the first step. Factoring always is greatest common factor. And we have a cotangent x. So I'm left with cosine squared x minus 2. Once it is factored, now I can separate the factors and I can set each factor equal to 0 and solve for each factor. So where's cotangent x equal to 0? No, that's where it's undefined. It's going to be 0. No, that's where it's undefined. From 0 to pi, at the ends of it, it's undefined. So it's got to be, So pi over 2 to 3, and 3 pi over 2 would be where it is 0. Okay, and then the second part, where is, oh, I didn't solve it yet. Cosine squared x equals 2. So I need to square root both sides with a plus minus. So now I have cosine x equals plus minus square root 2. So where is the cosine plus or minus square root 2? Nowhere. Why?
Because cosine can't be greater than 1.
Cosine cannot be greater than 1. Cosine x has to be less than or equal to 1. 1's the highest number it can possibly be. So this would just be like information that doesn't give me an answer. So we just have 2 answers. And then the general solution for that would be pi over 2 plus, what's the period of cotangent? What's the period for pi? N, where n is a integer. Do I need to put the second one? Why not? Okay, I just hear a bunch of like mumbling. Can somebody like volunteer the answer? Sam? Right. So this one already includes my second answer. Good. Okay. Now we've got factoring of the quadratic type. So if you have trouble seeing how to factor this, there's something called U substitution, where you can say U equals sine x, and every place you see a sine x, make it into a U. So we would have 2u squared minus u minus 1. And then you could factor that. And wherever we see a u in our answer, we'll change it back to a sine x. I know for sure that it's 1's at the end. I know for sure it's going to start with a 2 or a 1. I just have to figure out the correct signs. It's just factoring. So if you factored it using a u, I'm gonna put it I'll just put it in a different color right above it. If you factored it using a 2, you would get like 2u plus 1 and u minus 1, and then you would just take the u and just make it into sine x again. If you can't see the factoring when there's signs and stuff in there. Okay, so then we're going to set each factor equal to 0. Solve for each factor. There we go. So I think we already talked about this first one. Where is sine x negative a half? Where is sine x negative a half? Did we not talk about this yet? Where is it?
7 pi over 6 and 11 pi over 6.
All right, 7 pi over 6, 11 pi over 6. And then the other question is, where is sine positive 1? Right at pi over 2. So we have 3 answers. This one just says to put it in the interval from 0 to 2 pi, so I don't need to do the general for these. But you do want to put them in order. So if you're not sure the order, you just think about going around the circle, and pi over 2 would be first. And then we would come to that 7 pi over 6, and then we come to the 11 pi over 6. I must be just zoomed in really far. There's the next one. Okay. The next one is an example where we will use identities to make this easier to solve. If I look at it right now, it's not, I don't know how to solve it the way it is because I've got sines and cosines. So if I can use identities, I might be able to make them all the same trigonometric function. Does anybody know any identities that change sine into cosine or cosine into sine? Needed to know it for your quiz today. Eden.
Sine squared is 1 minus cosine squared.
Okay, so I'm going to do 2, 1 minus cosine squared plus 3 cosine x minus 3 equals 0. And then I'm going to distribute. I'm going to collect like terms. And once I have it in this kind of quadratic type form, I'm thinking I'm going to try to factor it. But because I'm going to try to factor it, that negative out front is driving me nuts. So I'm just going to divide both sides by -1. So I don't have to deal with it. Does dividing by -1 affect the answer? It does not affect the answer. As long as you do it to both sides, it doesn't affect the answer. If I have a graph like a parabola that's facing up and I change all the signs to negative, it'll just be, or if it's facing down, it'll be facing up, or if it's facing up, it'll be facing down. But the x values would still be the x-intercepts and they wouldn't change. So we would keep those x-intercepts the same. All right, let me try factoring this bad boy. You can use substitution if you need it. For this one, they're both going to be -1 because of sines and what that number is. And it's got to be a 2 cosine and a regular cosine. It's like my only options. I just need to make sure that it actually factors, because if it doesn't factor, we need to figure out the answer a different way. So I'm going to check my factoring. Yep, that worked. So I'll set each factor equal to 0. How am I writing my answers? Oh, the interval. So where is cosine x a half? Where is cosine x a half? Sanjay. Pi over what? 2? At 90 degrees? No. It's got to be a 30, 60, 90. No, it's not 30. Pi over 3. And what's this one down here? 5 pi over 3. And then where is cosine? I'm just going to use the same graph. Where is cosine 1? 0. Are we including 0 or are we including 2 pi? What's the directions say? Both? That's got to be a typo on my end. Where's this question? Oh, yeah, that's a typo. Sorry about that. They're not going to ask you to do both. Okay, so just 0. So x equals, put them in order. We'll start with 0, pi over 3, and then 5 pi over 3. Did I do that on other ones? Did I just copy and paste it wrong on every single one? I did. Oops, I didn't even notice it till then. I didn't even notice in my first class. Yeah, I was copy and pasting, so oopsies. I promise I didn't type it wrong that many times. I copy and pasted it. Okay, so I guess the rest of them are probably wrong because that's what I did. All right, next one. Now, this one is a little bit trickier than the rest. We're going to find all the solutions for cosine x plus 1 equals sine x on the interval from 0 to 2 pi, where it's not including 2 pi. Can I change cosine plus 1 into sine x? Can I change sine x into cosine x? No, because it's not squared. The only way to change sine or cosine into each other is if they're squared. So I'm going to do something dangerous here. I'm allowed to do it. Did you know what I was going to do? I'm going to square both sides. Okay, but you got to be careful though. Because originally, if the degree was like 1, we should only get like one set of numbers. Like if the power on the x is 1, we should get one set of numbers. But now when the power is 2, we're going to get more sets of numbers. But we need to find the numbers that satisfy the original equation. So there's an extra step if you do something like square both sides. There will be an extra step for this one before we get too far into it, especially if you've worked ahead. All right, so I'm going to square both sides. And when I square cosine x plus 1, that's where I like write it twice and multiply it out to avoid killing a poor little puppy. You don't want a puppy to die, right? Right? Okay, so we got to multiply it out. We get cosine squared x plus 2 cosine x plus 1. On the other side, this one's just sine squared x. Now that I have sine squared x in there, I can change it to cosine by doing the Pythagorean identity. 1 minus cosine squared x. I prefer to try factoring if it's possible, so I'm going to go ahead and try to see if this is factorable. I'm going to set it equal to 0. I'm going to move the cosine and the 1 over. And I get 2 cosine squared x plus 2 cosine x. Is that factorable? GCF? 2 cosine x? So we have 2 cosine x equals 0. Cosine x plus 1 equals 0. Okay. So I told you this one was dangerous though, because I actually found more solutions than I would normally have. I found more solutions that would would satisfy the original one. I don't know what word I'm supposed to use there. Anyway, so what you have to do is you have to check your solutions. We have to check for extraneous solutions. And if this is by hand, you're going to be checking it by hand. Like if you don't get a calculator, then you're going to check this by hand. So I'm just going to take each solution. We've got, what it was the first one, pi over 2, and 3 pi over 2, and pi. And we're just going to plug each of those into the original question. So cosine pi over 2 plus 1 equals sine pi over 2. So cosine pi over 2 is 0 plus 1 equals sine of pi over 2 is 1. That one's good. 3 pi over 2, so cosine 3 pi over 2 plus 1 has to be sine 3 pi over 2. So 0 plus 1 equals -1. Not equal. This one doesn't work. And then cosine pi plus 1 equals sine pi. Cosine at pi is -1 plus 1 equals sine at pi is 0. That one does work. So our answers for this will be pi over 2 and pi. If we have an extra second, which I don't know if we will, but if we have an extra second while I'm doing these notes, I'll show you how you can check them. But I'm pretty sure does it go over checking? Maybe not. But you can, oh yeah, it does. It does in the book over by example 2. You could use your graphing calculator to graph each side. Like you would graph cosine x plus 1 and graph sine x plus 1 and see where they intersect from 0 to 2 pi. So you'd set your window from 0 to 2 pi. All right, function of multiple angles. And I see we only have 2 minutes, but I will keep recording the video once the bell rings for anybody who needs to leave early. I'm going to finish the notes on the video. Okay, functions of multiple angles. Find all the solutions of 2 cosine 3t minus 1 equals 0. So first thing I'm going to do is get cosine 3t by itself. You see how there's a 3 in a spot where we didn't have any numbers prior to just a moment ago? Okay. So I'm going to have cosine 3t, and I move the 1 over, and then I get divide by 2, and I get cosine 3t equals 1/2. So on the interval from 0 to 2 pi, 3t, this angle, what angles would it be for 1/2? It'd be here and here. What angles would that be? It's going to be pi over 3 and 5 pi over 3. You know what? We're going to be finding all the solutions. So I'm going to use that one. Okay, we're going to find all the solutions. It doesn't say what to do, so we're going to find all, which means the general solutions. So what I'm going to do is I'm going to find it on the interval from 0 to 2 pi. That's where I'm going to start. Oops. From 0 to 2 pi, I'm going to start there. And I get pi over 3, and I get 5 pi over 3. Then after we have that, then we will solve for t. Actually, let me do the general solution first. General solution first. So 3t for all the solutions. This is cosine. It is 2 pi for the period, so 2 pi n. And then I'm just going to put off to the side here because it's going to get too crazy looking over here. Okay. So we've got pi over 3 plus 2 pi n and 5 pi over 3 plus 2 pi n. Now at this point, I'm going to solve for actual t. So I'm going to just divide everything by 3, both sides. So we will have that t equals pi over 9 plus 2 pi n over 3. And t equals 5 pi over 9 plus 2 pi n over 3. What does that 3 actually do to the normal cosine graph? It shrinks it. So we'll have them like closer together. So that's why the period is now 2/3 what it would normally be. And the first and second values are scrunched in closer to the x-axis than they would normally be. All right, example 8 is very similar to example 7. We're going to find all the values, all the solutions of 3 tangent x over 2 plus 3 equals 0. So I'm going to get tangent x over 2 by itself first. So I'm going to subtract that 3, divide by 3. I get -1. So x over 2 would have to be, where is tangent -1? From 0 to 2 pi. Three pi over 4. And then tangent has a period of pi. And then the second one would be 7 pi over 4 plus pi n. So that would be the general solution. But once we actually solve it for x, what do I need to do to solve for x? Right, we're going to multiply both sides by 2. Oh, wait, it's tangent, though. So I don't even need the second one. Sorry, my bad. I wasn't even thinking. So it's tangent. I only need the first one because the other one already is pi. Okay, so I just need the first one. And so I get x equals 3 pi over 2 plus 2 pi n. N is an integer. And if you guys write 2n pi, that's totally fine. I'll always put like both answers. All right, there's just one last one. Using inverse functions, find all the solutions of secant squared x minus 2, tangent x equals 4. So since we've got secants and tangents at the same time, I feel like I want to change them using those Pythagorean identities. Does anybody remember the Pythagorean identity for the one? Okay. Are we sure today? I'm going to go ahead and just subtract that 4 while I'm at it. So we have tangent squared x minus 2 tangent x minus 3. We get. So is that factorable? Yep, factors. So then I have tangent x equals 3 and tangent x equals -1. So for this one, x would equal, are we doing this on a certain, I have all. Okay. Right? I wrote all. Yeah. Oopsies. Where's tangent? -1. 3π/4. And then if I add the period on the pi, that ends up giving me the other one. So I don't really need to write the other one because we're doing general solutions. So I just need to add on pi n. Okay. What about the other one? Everybody know where tangent is 3? So this is what they mean by using inverse functions. We can get x by itself by saying like it's equal to arctan 3. That is in the first quadrant. It's positive. It's in the first quadrant. Arctan 3 plus, what's the period? Pi n, where... Now, if I need to know what this number is specifically, what would I need to do? Pull out my calculator and do second tangent 3, and then I could actually know what that number is specifically, but we can write it like that because that's where it is at arctan. Okay, so the assignments are written on the module, and thank you for being patient while I got through the rest of the notes.